Just to give you some context, this is a physics project I did in late May of this year. There's a volume error I made on this upcoming clip. I would recommend you turn your volume down. Regular viewers of this channel might recognize a familiar meme at the end. Thank you for watching and enjoy.
Ooh, I would not want to be that guy. Or that train.
Let's find the kinetic energy of the transit train. The formula for kinetic energy is 1/2 mass times velocity squared. The mass of the transit train is 38,600 kilograms. And the velocity of it is 24.5872 meters per second, or 55 miles per hour. Let's jump right in to the calculations. So I've been plugging in the numbers, and as you can see, I simply put 38,600 in with M, and then put 24.5872 meters per second for the velocity being squared is 604 meters per second squared. The result for the acceleration is 604 meters per second squared. And half of the mass is 19,300 kilograms.
In total, the amount of kinetic energy that is hitting Mr. Incredible at this time is over 11 million newtons, and it only takes 2,300 newtons to break a human skull.
Yeah, that's pretty incredible. You may be wondering, how are you able to see this video? Well, it has to do with pixels.
Pixels?
Now, a pixel is a tiny fluorescent lamp switched on or off electronically using liquid crystals to rotate polarized light. Now, you may be asking yourself, what does this have to do with a pixel? Well, each pixel in an LCD screen or a liquid crystal display has a crystal that rotates, which polarizes the light waves in either the X or Y plane. As you can see, the light wave traveling on the X-axis is blue, and the light wave traveling on the Y-axis is red. I'll get into the importance of those later. But now, let's get into the specifics of polarization. The definition of polarization is the action of restricting the vibrations of a transverse wave, especially light, wholly or partially in one direction. As you can see from the planes I've drawn, I was trying to depict what polarized and unpolarized light looks like. Polarized light is to the left, and unpolarized light is to the right. Now, blue is the sound wave traveling on the x-axis, and red is the sound wave traveling on the y-axis. As you can see, when you're looking at the polarized plane, only one plane is being hit with light waves. But if you look to your right and look at the unpolarized plane, you see that both planes are getting hit by light waves. Now, the difference between the two is that polarized light is traveling in one plane, like X. However, unpolarized light is when the light wave is traveling in both planes, the X and Y. Now, since Bubbycast is a podcast, we use pitch tweaking a lot. And the definition for pitch is how high or low the sound being emitted is. And some visual examples of pitch. An example of a sound wave with a low pitch is to your left, which, as you can see, the wavelength is longer, while an example of a high-pitched sound wave is to your right, and the wavelengths are very short.
And you get something that makes it sound like a chipmunk.
And then if you have a low-pitch sound, it sounds very smooth. Low pitch.
Now for our next topic.
It's frequency.
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 The definition of frequency is the rate at which a vibration occurs that constitutes a wave, either in a material, as in sound waves, or an electromagnetic field, as in radio waves and light, usually measured per second.
Fantastically fun frequency facts.
The frequency of a microwave is 2,450 hertz, and the frequency of a Wi-Fi wave is 2,417 hertz. Furthermore, Wi-Fi waves can reach up to 5,000 hertz.
5,000 hertz.
And dogs can hear 45,000 more hertz than humans, which have a cap at 20,000 hertz. Speaking of frequency, there's something called the Doppler Effect. The definition of the Doppler Effect is an increase or decrease in the frequency of sound, light, or other waves as the source of the observer moves towards or away from each other. This effect causes sudden change in pitch noticeable in a passing siren, as well as the redshift seen by astronomers. Now here's a poorly drawn example of the Doppler effect. So Bubby number 1 is in the car, and the position of me, Bubby number 2, at position 1, causes me to interpret a lower pitch because I'm further away from the source of the sound waves, which is the engine. Now if I skedaddle over to position 2, I am closer to the source, and I interpret a higher pitch. Now for our next topic, redshift. The definition of redshift is the displacement of spectral lines towards longer wavelengths.
The red end of the spectrum.
In radiation from distant galaxies and celestial objects. This is interpreted as a Doppler shift, sounds familiar, that is proportional to the velocity of recession and thus to distance.
And basically what this means is that the farther light waves are away in space, the more they have this reddish hue to them.
Yeah.
Which is why it's called redshift.
Yes, and there can even be blue shift. As you can see from the graph, the red end of the spectrum has a longer wavelength, and the blue end of the spectrum has a shorter wavelength.
So if you've been listening to this video, you might wonder, how have you been hearing all these random sounds? Well, let me tell you, it's from speakers.
How a speaker works. When a fluctuating electric current flows through a coil, it becomes a temporary electromagnet, A, and is attracted and repelled by a permanent magnet, B.
It's a big magnet.
As the coil moves, it moves the cone back and forth, pumping sound waves into the air.
C.
Yeah, so this is another poorly drawn example, a Bubby drawn example. But I was trying to show you where the sound waves hit. And the sound waves hit the cone, and the cone moves back and forth. But how can you find the intensity of sound? You could use a unit called decibels. The definition of decibels is a unit used to measure the intensity of sound or the power level of an electrical signal by comparing it with a given level on a logarithmic scale.
Some examples.
Normal conversations. Hey, Bubby, how are you doing? 60 to 70 decibels.
That's not too loud.
Subway trains, 90 decibels.
It's a little loud.
Jackhammer, 100 decibels.
It's pretty loud.
Standard headphones or earbuds at full volume, fully cranked, 110 decibels. Power saws and power tools are at the same decibel as fully cranked headphones.
Turn your headphones down.
110 decibels.
This is also a public service announcement. Turn those headphones down.
A cowbell at 0.6 meters or about 2 feet is 110 decibels.
Stop playing with cowbells, too.
Live rock music, 108 to 114 decibels.
Might as well stop going to concerts.
Turbofan aircraft at takeoff power at 200 feet is 118 decibels. Thunder in a close proximity to the ground stroke is about 120 decibels. Fun fact, we actually witnessed a ground stroke when we were at the beach.
Classic.
It was pretty powerful.
We got so excited we set off our air horns.
Which air horns have 129 decibels.
Race cars, 130 decibels. Train horns, 140, 152.
Fireworks, 150 decibels.
So basically, always wear ear protection. Or you might get hearing loss, which happens due to damage of the inner ear, as well as
Aging and exposure to loud noise may cause wear and tear to the hairs and nerve cells in the cochlea, the spiral cavity in the inner ear containing the organ of Corti, which produces nerve impulses in response to sound vibrations that send the sound signals to the brain. When these hairs and nerve cells are damaged or missing, electrical signals aren't transmitted as effectively and hearing loss occurs. Now, how the heck does sound get interpreted by brain? Well, thanks for asking. The tiny hair cells in your inner ear send electrical signals to the auditory nerve, which is connected to the auditory center of the brain, where the electrical impulses are perceived by the brain as sound.
The answer is it's all electricity in your head.
The long-term exposure to anything between 90 and 95 decibels can cause hearing loss, experts say. Furthermore, 150 decibels is usually considered enough to burst your eardrums, and the threshold for death is around 185 to 200 decibels.
You can die from sound. That's metal.
Finally, let's see if you can use your newfound knowledge to estimate the velocity of this next clip.